In this video, I am going to show you the complete design and detailed drawing of flat slab with drop panels, also calculation of the sizes. The given scenario is shown. The FC prime is 5 ksi, yield strength of steel is 60 ksi, floor height is 10 feet. We have to design the first floor. The column dimensions are given as 18 by 24. Center to center span of the columns is 12 feet. The plinth level is 6 feet from the base of the structure. The plinth beam are of 12 by 24. The occupancy of the structure is residential. Super dead load or SDL is 36 psf. We have to calculate the thickness of the slab and drop panels. Also, we have to calculate the drop dimensions and its steel. We have to use UPC 97 for the loads and ACI code for design. The cantilever part of the slab is 4 feet as shown. Starting with calculation of the slab thickness, we use the ACI 31808 table. The slab in our given scenario is with drop panel. Starting with the exterior panel thickness calculations without edge beams, it is the fraction of 1/30th of the span. The interior panel thickness is 1/36th of this panel. So conservatively, for keeping the slab thickness uniform, we take it as 5 inches. The long-term deflection limit for flat plate and flat slabs is L by 240, where L is 12 feet in our case. So the deflection limit is 0.6 inches. Open ETABS. We start with defining the grids in ETABS. Number of stories are 3. The typical story height is 10 feet as given. We may also directly click on flat slab, but it's okay that I can show how to model the drop panels. Now we need to add the plinth level. Let's call this as plinth level. The height is 6 feet from the base of the structure. The story 2 is first floor, or basically it's ground floor slab. First floor and the second floor, or the roof slab. Click on OK. Since the elevations are revised, so we have to go to the new second floor now. Start by defining the material properties for concrete and steel. Your strength is 5 ksi, which we required. The normal weight concrete is 150 pound per foot cube. Okay. Now we need to add the rebar material. Grade 60, which is, so here it is 60 ksi, which is okay. Let's rename this as G60 deformed so that we can identify which material we have defined for our particular case. Now defining the slab sections, which was calculated as 5 inches uniform thickness for the slab. Selecting the material for the slab and the thickness of the slab. In order to understand the difference between shell thin and membrane, you need to go to the previous video whose link is given in the description. So that you get an idea when to check the membrane option and when to check the shell thin option. Right now I am assuming we have gone through that video, so it's shell thin. We need to set the property modifiers to incorporate the crack moment of inertia for the slab according to ACI code, which is 0.25 for bending direction. So now we are done with defining the slab. Let's add the property of the drop panel. Now we need to calculate the dimensions of the drop panel. The drop panel of the dimensions are A and B. Let's call A the dimension parallel to the span length L1, which is 12 feet in our case. So A is basically span length divided by 3, and B is also a span length parallel to the dimension divided by 3. So which is 12 feet in our case in both directions. So the panel is 4 feet by 4 feet. The thickness of drop panel is usually taken as thumb rule as quarter of slab thickness, which comes 2 inches in our case. The thickness of drop panel can be greater than that, but at least quarter of the slab thickness is necessary. So you see we have defined as 7 inches, which includes slab as well as drop thickness in the region. The property modifiers of the drop will be similar to that of slab. The important point here was that we took 7 inches, which included slab as well as drop panel, for that region where the drop panel is to be drawn. Now we need to define the section properties for the frame, that is beams and columns. The column dimensions were given as 18 by 24. The material was 5 KSI. The property modifiers according to ACI code for columns is 70% of the gross moment of inertia. So that if the cracking occurs, we are already incorporating that in terms of reduced moment of inertia. So select the steel material which you defined. Reinforcement to be designed. Okay. Now we need to add the material or frame section for the plinth beam. Let's call this as B12 by 12. Selecting the material for the plinth beam. The width of the beam is 12 inches and the depth is 24 inches as given. Select beam design. Go for the steel selection which you already defined. The property modifiers for the beam according to ACI code are 0.35 of the gross moment of inertia. The torsional value we took is 0.001 usually, making the beam torsionally flexible, as we want the slab to absorb all the torsional moments and the beam not to incorporate the torsion reinforcement. Here in our case there is no slab attached to the beam, so the columns will take all the moment, which will create a torsion in the beam, for which we don't want to design in our particular case. Now you may delete the rest of the frame sections which are useless to you, so that the modeling will be easier and selection of your cross sections from the list will be a lot easier to find. Now we need to draw the columns first. Select your column. Since the orientation does not seem the right way as we were given in the scenario, so we need to change the angle of the column as 90 degrees, or you may simply define the column as 18 by 24 or 24 by 18. Both are same. Now it's your choice, either you draw the columns on the intersection of the grids, or if the columns are located on the intersection of the grid lines, so you may use a shorter method, that is drag the window and the columns will be drawn at the intersection of the grids. Now we need to draw the none lines first. The cantilever part was of 4 feet, so it becomes 48 inches. So we draw the none lines as the boundaries of the slab, which we will be drawing. So we are drawing the slab right now, or you can say the slab panels. If the slab is located between the grids, you may use a similar easier option which requires just a simple click, or drag the window and the slab will be drawn between the grids. Now you need to draw the cantilever part slab. Draw one panel and you can copy or replicate using the ETABS replicate option. For that you need to select the slab, go to edit and replicate it using the dy, since we have to replicate parallel to the y dimension. It's minus 12 feet. Let's call it as numbers 4. Okay. Now we have to do the similar thing on the other side as well. First we draw one single panel. Actually the line should be accurately perpendicular so that it comes in its own panel place. Now we replicate it in similar manner. 4 numbers in negative y direction. Now we need to mesh the slab. In order to understand the meshing of the slab accurately, you need to go to the link of the video given in description for manual and auto meshing options. For now, we need to divide the slab. The meshing shall be at most of 3 feet by 3 feet areas, not larger than that, so that the results may not be accurate. So 12 feet span divided by 3 gives us 4 by 4 areas at least. The finer the meshing, the more accurate will be the results. If you divide it in 5 by 5 areas, the more accurate will be the results. But 4 by 4 areas is the limit here, as it gives us 3 feet by 3 feet dimension small squares. Now since the meshing shall be continuous so that the displacements are accurate, we need to extend the joints to form meshing in the cantilever area. So the cantilever area has extended meshing now. Similarly, we are doing the same meshing procedure for the other side as well. Apply. Now select the cantilever part, which is of 4 feet and shall be meshed in 2 areas at least in X direction. Press OK. Now go for the other side. Shall we do done with? Okay. Actually, it was not selected previously. 2 feet by 1 feet. Click on apply. Okay. Now we have meshed the slab. You may also have used auto meshing option, for which you need proper understanding. Click on the previous video whose link is given in description. Now going to the load patterns, we need to define the load pattern for the finishes, which we have done defining. The self-weight multiplier shall be 0 because we will already specify the load, while the dead load includes the load of the structure, which is calculated by ETABS itself using the dimensions. Now you have to select the slab for assigning the loads, or just a minute. First we need to model the drop panels. The drop panel dimensions which we calculated are 4 feet by 4 feet. So on each side of the column it will be of 24 inches right and left. So we will draw dummy lines so that we can demark the drop panel boundaries. Which is having an offset of 24 inches. So we are done doing it in y direction. Now we have to do the similar thing in the other direction of the axis, so that we have a complete set of drop panels formed by the intersection of these lines. But before that, you have to select the slab as a whole and match the slab at these lines, so that we can delete the areas between these lines for the drop to be drawn between them. Now go to edit and mesh or divide the slabs. Cookie cut and extend. Click on apply. So now you can see the areas between the lines is now separated from the rest of the slab, which we can now delete and draw the drop panels, which is accurately 4 feet by 4 feet area, or 48 inches by 48 inches, like we draw in terms of inches. Now press the delete button from the keyboard. Now draw the drop panel, which is of 2 inches, but including slab thickness it is of 7 inches. The exterior drops are to be modeled. You may use simply the replicate command if you are good in using it. Otherwise, a drop may be assigned twice. For example, I am showing you what mistake you may cause error. First, you need to edit and divide the drops into 3 feet by 3 feet areas at least, which gives you 2 by 2 areas. So now we need to replicate the drops. So you see, I have added by mistake an extra drop which had to be deleted. So now replicating in other axis direction, giving it 3 numbers. When you hover the cursor over the apply option, it gives you a preview. Now I am going to replicate it in dy direction, and that is minus 12 feet. So now we have got the preview which we exactly require. Now you can view the drop distinguished from the other slab by clicking on the colors set by the section properties. You may change the color of the drops. First, delete the null lines. If it's not deleting, then click on a single null line, deselect it and reselect it. Actually, it's a glitch in the software. Now reselect that line and press delete so that these lines will be deleted, which we do not need any now. They were only for drawing or helping us to demark the boundaries. Now you may change the slab color. Refresh the view. So now you can see the drop are in gray color and the slab is in purple or blue color, you can say. Now select the whole slab. Or you can go with the selection option. Assign the loads. The super dead load for the finishes is given as 36 psf. Replace existing loads. Now we need to again select the slab and assign the live load. Since the structure is in residential occupancy, so we need to use the loading code UBC97 for that, given in our case, which gives us 40 psf as live load for the residential structural category. So now we are to assign 40 psf load. Click on apply. You can verify the loads by right clicking on the panel. So now we need to select the slab as a whole and assign the diaphragms to the slab. Since it is concrete, then the diaphragm selected shall be rigid so that it transfers the forces or lateral forces in the direction according to the stiffness of the columns. For slab design, it is not really important to apply the earthquake or wind loads if it's not a high-rise structure, because the slab does not usually takes lateral forces, and if it takes, it is extremely rigid in that direction for which the concrete is sufficient. Now we need to replicate the slab on the other floors except the plinth level, where only plain beams and columns are present. We need to set to the default viewing options. Go to plinth level. The columns are not replicated here, so we need to replicate the columns. Hide everything except the columns. So you see 24 frames selected. Other things are not selected, which may cause doubling. Now we have replicated. We have to replicate the column. So you see the columns are straight, there is no issue in the modeling. Set to default viewing options, click on apply. Now we need to draw the plane beams in the bottommost story or the plinth level. I'm going to show you how to quickly draw the plane beams. In the case, drag the window and the plane beams will be formed at the grids. Now we need to assign the diaphragm to the replicated stories, as the replication would not have included diaphragm, which we could have selected, but we missed that. Now the slab selection design code is ACI 31808 as given to us. You may change the slab cover for reinforcement here as per your requirements. We need to add the default design combinations, which will be added according to the design code which we selected. 1.4 times of the dead loads and a combination of live and dead by a factor of 1.2 and 1.6 respectively. Now the next step will be adding a long-term deflection combination so that we may apply the check for the deflection on the slab. Which involves a factor of 3 for the dead loads usually, conservatively, and a factor of 1.5 for the live loads. Now you need to draw the design strips starting with column strip and middle strip. Now first we need to calculate the strip width. Column strip width is quarter of the clear span in the shorter direction, but in our case both the directions are of 12 feet, so that it becomes 12 feet divided by 4 gives us 3 feet and 36 inches in each span. Width of the middle strip is the remainder of what is left after drawing the column strip in the spans. Let's take 36-inch width for the column strip in each span. You may also view the strip width by using other assignment and show width option, so that you can get a clear idea of what you are drawing. Go for the middle strip. Remainder is 36 inches here. Now for the leftover areas, you may extend the column strip, as negative movement will be governing here. Actually, it had to be this way. You can always learn this by practice whether to add in right or left. Now add 0 for the corner strips. It is not necessary that the dimension of middle strip remains constant in both the spans, but it is necessary for the column strip that dimensions remain constant in both directions. So now we need to assign the steel material to the strips. Let's turn on the strip layer A only. Go to strip base and select your steel which you defined. Now selecting the middle strip and repeating the procedure. Select the steel which you defined, press OK. Now turn on layer B, starting with middle strip this time. Select the material for the steel so that it gives area of steel with respect to the yield strength specified. Press OK. Now we are done with assigning the material. You may note that we have drawn the strips only in the first floor because we are required to model the or design the structure for the first floor only. Now we need to run and save the analysis model. So the analysis is now run. You may check first the long-term deflection. Click on undeformed shape, display deformed shape, draw contours in Z direction because we are interested in deflection due to gravity loads right now. So on the left bottom of the screen, you may see the absolute terms of the deflection. So your deflection is minus 0.5, which is within the limits. The limits were 0.6. So now we are okay with the deflection check. So now we need to design this slab so that we can check the punching shear in ETABS as well as in Excel. So the slab is now designed. Go for the punching shear check. The number here are shown should be less than 1, or you may go for a cross check. Pick up a critical value or the highest value you see but less than 1. Right click on the center point of the column and you may see the punching shear parameters and properties. Use the Excel sheet given in the description of this video, which is in SI system. So the dimensions and the forces shall be entered in mm and kilonewton. The thickness of slab is 7 inches in this region, so that is 175 mm. The effective depth, let's take the cover as 1 inches conservatively, so the effective depth is 150 mm. The dimension of the column in X direction is 24 inches or 600, and in Y direction it is 18 inches, that is 450 mm. The yield strength of steel is 60 ksi, that means 420 MPa, and the FC prime is 5 ksi, that means 35 megapascals. Pu shall be taken as the shear force given in the parameters, that is 9.9 kip. Let's convert it into SI system. So the shear force now is 44.1 kilonewton. First, revise the effective width of the slab according to the ETABS 139.7. Ignore the red depth not sufficient error right now. I will tell you in detail. Shear force is 44 kilonewton. The moment in major and minor directions shall be noted properly. In minor direction it is 4 point something, and in major direction it's 9.17. So now we have to see whether the concrete is sufficient. So punching shear reinforcement is not required. Since the punching shear reinforcement is not required, so the error depth is not sufficient for shear reinforcement is not valid to us, because we are not providing any shear reinforcement, so we don't need to provide that amount of depth for the shear reinforcement. No shear reinforcement is required because. Now display the flexural design. Impose minimum reinforcement so that according to the slab cross section we get minimum reinforcement. Turn on top, bottom rebar and layer A and B all at once so that you may set a proper meshing. First we need to use the inch system. Use US default system that converts it into inches. Now again go to the display design. Since there is a glitch in ETABS, you may click on none and typical uniform reinforcement again. There the option is unlocked. Let's take the spacing as 8 inches for number 3 bars. You may increase the scale factor for the drawing. So not very high reinforcement. So we are getting a very nominal steel in the drop panel. You may also increase the graphic font size for clear visibility. So now we can see the numbers of bars required. That means the bars are very less required as extra reinforcement in the drops. So I may have to increase the spacing of the mesh. That means I have provided extra mesh which was not even required. So now we need to increase the thickness. Note that the blue color is the reinforcing bar and the black color, when you hover it, black colored line is the distribution of that bar. Let's take it as 12 inches. So now we are getting a decent number of bars in the drop panel, that is 5 number 3, 4 number 3, 7 number 3, which is okay. You may also round up the number of bars to an odd number. Let's say we may round up 6 bars of number 3 to 7 bars. Usually designers use a thumb rule that in both the direction they provide higher number of bars, but here we will design what is given by the ETABS. So we are getting 6 number 3 bars and to be distributed as the black line shows. The detailing of the bar is done as such that the top reinforcement is at least 1/3 of the span in both directions, and the bottom reinforcement is from supports to the next support. So I have divided the slab into layer A and layer B, which we will later combine when the drawings are finalized. Just for demonstration purposes, so that it's easier to understand, I have drawn two plans. First is for layer A of reinforcement and other is layer B of reinforcement. Layer A and B depend on the strip directions assigned, which will give the steel direction using direct design method. So first we display the steel in layer A. So the reinforcement required here is shown. The blue color is the reinforcing bar. So this is layer A shown in ETABS. We need to now label the steel in AutoCAD. Note the numbers of the steel bars required. As I said, you may round up the number of bars. Let's start detailing with the AutoCAD drawing. And later on we will print this drawing and show how to actually print the drawing in PDF format. So you see the labeling is simple. There is no hard and fast rule for the spacing of the extra bars. The spacing check applies, or the minimum spacing check applies to the main reinforcement, which we already incorporated by clicking on Impose Minimum Reinforcement option in the display flexure design of the slab. Actually, we have to edit the slab mesh, the mesh which we selected. By looking at the bars, that extra bars are not so high or not too low. Luckily, we are not getting any extra bottom reinforcement here. The only reinforcement required in extra terms is the top reinforcement. Usually the mesh is sufficient for the bottom reinforcement requirements for flexure. So we are almost done in labeling the reinforcement layer B of the slab. So now we are done here. Now click on the zoom option, press Ctrl and P and convert it into AutoCAD. Click on apply to layout and close the window. Now you may set the appropriate viewport. Now click Ctrl P, OK. Now your PDF has been published, which I saved on desktop. So you see, this is how we can also print the diagram into the paper or edit in AutoCAD. Thank you for watching. Please subscribe to the channel and watch complete ETABS tutorial videos and much more to come.